6, this is another gas law problem. They give us the volume of the gas, the temperature of the gas, and the pressure of the gas, and they're asking for moles. So on your equation sheet, you're going to go and look for the equation that has volume, temperature, pressure, and N for moles, and that's PV equals nRT. Also on the equation sheet is the R constant, which is 0.0821. The units in the R constant are liters times atmospheres over moles times Kelvin. So when you plug in the units for these variables, you want to make sure that they're in those units. So the volume's in liters, the pressure's in atmospheres, but we want to change the temperature to Kelvin. So we're going to add 273 to 32 degrees Celsius. So that is 305 Kelvin. So then we can plug in the values. The pressure is 5.5 atmospheres. The volume is 95.2 liters. The N is our unknown. The R is 0.0821. And the temperature is 305 Kelvin. So to solve for this in our calculator, we're going to do 5.5 times 95.2. And then we're going to divide it by the product of 0.0821 times 305. So if you're doing it all in one step, make sure you put parentheses around the 0.0821 and the 305. And that will give us the number of moles, which works out to be 20.9. Okay, so again, that equation's on your equation sheet, the R constant's on your equation sheet. You do need to know that you should change degrees Celsius to Kelvin by adding 273. Okay, the next problem talks about volume and molarity of a solution. So they give you the volume in milliliters and they give you the molarity and they ask you for moles. So on your equation sheet, it does give you the equation that molarity equals moles per liter. And you certainly could use that to solve for it. But if you remember in class, I encouraged you to remember that instead of using capital M, we're going to change that to be 0.5 moles, 0.55 moles per liter. Which means if you have 1 liter of the solution, that's going to have 0.55 moles, which makes this an equivalence, which you can put that into the conversion factor. So I'm going to start with 1,550 milliliters and put that over 1. And I'm going to show changing it to liters first, because molarity is moles per liter. So we want to know how many liters we have. So there's 1,000 milliliters in 1 liter. And then we're ready to use our molarity. We're going to put 0.55 moles over 1 liter. So the milliliters will cancel out, the liters will cancel out, and this will give us the moles that we're looking for. So that works out to be 0.85 moles of the solute LIBR. Okay, so remember, if you see capital M, that's the same thing as moles per liter. Right, number 8 is also another question involving solutions. So it's giving us the percent by mass, and it's asking us how many grams of sucrose, which is going to be the solute, are in a total mass of the solution of 475. So you might realize that this is just taking a percentage of a number. If you know the total mass is 475, 15.5% of that mass is the solute. So you can take a percentage and turn it into a decimal by dividing by 1,000, and then just simply multiply by the total mass. If you know the total mass and you know the percentage, you're just taking the percentage of that number, which works out to be 73.6. If you have trouble remembering that, again, on your equation sheet, it gives you that percent mass of a solution is equal to the grams of solute over the grams of solution. It's always part over whole for percentage. If you remember doing percentages like when you first learned them, a really good trick is to just put that over 100. So like 15.5% is the same thing as 15.5 over 100. And then you can set up like a proportion. We don't know the grams of salt, that's our unknown, but the total solution weighs 475 grams. So this will give you the same answer and you're just cross multiplying. So mathematically you're doing 475 times 15.5 and then dividing by 1,000 to figure out what the solute is. And that's going to also work out to be 73.6 grams. Okay, we're on the last page, and these are things that we learned more recently. So this is a double replacement reaction, and in a double replacement reaction, there's usually what's called a precipitate, and the precipitate is the compound that's insoluble, and so it comes out of solution and forms a solid. So what you're going to do is you're going to look up the products, and you're going to find them on the equation sheet, which will have the solubility chart that we learned about before to tell you if something is soluble or insoluble. So when you go to look on your solubility chart, you'll find that the sodium nitrate is soluble, but the iron phosphate is soluble. So again, the one that's insoluble is going to be the one that comes out of solution and gets cloudy and forms the precipitate that we saw. So that's going to be S. The one that's soluble means that it's going to be in solution, and water is the solvent, so it's called an aqueous solution, so we use AQ for the symbol for that. All right, when we did this in class, what we did is we broke down everything to show all of the ions. So I'll walk through how to do that. Anything that was aqueous, you break it apart. And if there's any subscripts or coefficients that are assigned to it, you make sure that you kind of distribute them. So for this one here, it would be 3 sodium ions that are positive, plus a phosphate ion that's -3, plus an iron ion that's +3, plus 3 nitrate ions. Now you will have your ion sheet for help for the charges. And then over on the other side, the sodium nitrate is aqueous, so I'm going to show that broken up. But the iron phosphate is insoluble, that's the precipitate. So I'm going to keep that together as a compound. So if you remember doing this in class, there are spectator ions, which are the same on both sides. So the sodium is aqueous and broken apart on the left side as well as the right side, and so is the nitrate. All right, what we're really looking for here is what's called the net ionic equation, which is going to be this next step here. What I want to do is I want to show making the precipitate, which is the iron phosphate. So I'm going to show the iron and the phosphate on the left side broken apart, turning into the iron phosphate, which is a solid on the right side. So it's going to look like this. The iron ion that's +3 plus the phosphate ion that's -3 makes iron phosphate. This is what we're looking for. If you want to do the first step first and then cross things out to get this final one, that's fine, but we're really looking for this last step here. Okay, then it asks you to identify the spectator ions. So those are the ions that are not part of the precipitate. Those are the ions that are aqueous. So that would be the sodium ion and the nitrate ion. Those are aqueous before and they're aqueous afterwards, so nothing's happening to them. All right, in our last problem, we have 2 more problems. We have acid-base question. So when you go to find the pH of an acid or base, make sure you understand that this could be an acid or a base. So you should know that NaOH is a strong base, and when you put it in water, it dissociates and breaks apart completely. So if you have 1 sodium hydroxide, you will get 1 hydroxide. So what they give us is the molarity of the sodium hydroxide, which we can assume is the same as the molarity of the OH. So this here is going to match up with this. If they gave us HCl, it would have matched up with the hydronium concentration because it's an acid and forms hydronium ions. So make sure you're careful of that. So the OH concentration is going to be 2.7 times 10 to the negative fourth because that's the concentration of the sodium hydroxide. The next step, you can skip around here. It would be really hard for me to go right to A from this. I went to B, and now I'm going to go to D. If I know the hydroxide concentration, I can get the pOH by doing the negative log of the hydroxide concentration. Okay, there's going to be equations on your equation sheet that help you with the pH calculations. So I'm negative logging 2.7 times 10 to the negative 4. Right? Be careful putting that into your calculator. There's a log button, so you can do negative log and then type in 2.7 times 10 to the negative 4th. And we can round to the hundredth place. So that gives us 3.57, and that's what's called the pOH. So the next thing that would make sense to find is the pH. Right? The pH plus the pOH always equals 14. So because we know the pOH, we're going to do 14 minus that to get the pOH. So 14 minus 3.57 gives us 10.43. Now 10.43 is really the number that we care about when we talk about acids and bases, because that's the pH. Which makes sense because we have a base that we started with, so the pH should be greater than 7. Okay, we need to find one more thing, and that's the hydronium concentration. So I think the easiest thing to do from here is if you know the pH, you can find the hydronium concentration by doing like the opposite of negative log, and that is 10 to the negative. So the hydronium concentration is equal to 10 to the negative pH. So like if the pH was 3, the hydronium concentration would be 10 to the negative 3. Now because the pH is not a whole number, we want to fix this in our calculator. So what you want to do is 10 caret negative 10.43. And that will simplify it to you in the right form of scientific notation, which will give us 3.7 times 10 to the negative 11th for the hydronium concentration. So again, because it was a base, I went right to the hydroxide concentration first. And then once I knew the hydroxide concentration, which is what's given, then I went to the pOH. And then after that, I did the pH and then did the hydronium concentration. That would be the easiest order to complete that. Right, in our last question, we're doing a titration. There's an equation for titration. It's NaMaVa equals NbMbVb. Okay, one side is all about the acid, and the other side is all about the base. And we set them equal to each other because when you do a titration and you reach the equivalence point, the amount of H and OH are equal to each other. So the acid here is HCl, and the base here is SrOH2. The N comes from the formula. So it's really the number of H's. So in this formula, you only have one H, so the N here is going to be 1. And in this formula, you have 2 OH's, so the N is going to be 2 there. I'm going to write the reaction afterwards. So I'm going to go ahead and say that the volume of the base is 15.5, the molarity is 0.125, and then the acid volume is 22.5, and we're trying to find the molarity. So if the left side is the acid, I'm going to do 1 for the N times my unknown, I don't know the molarity, times 22.5 milliliters. Okay, that side was for the acid, and the other side's for the base. That's coming from here. I'm going to use 2 because there's 2 OH's. I'm going to use 0.125 because that's the molarity, times 15.5 for the volume. So in my calculator, I'm doing 2 times 0.125 times 15.5, and then I'm dividing by 22.5 to get the molarity by itself. And that works out to be 0.172 molarity. All right, for the neutralization reaction, I'm taking the HCl and adding it to the strontium hydroxide. And in neutralization, one of the products is water. So the H and the OH make water, and then you have two leftover ions. In this case, you have strontium and you have chloride. Now, with all the reactions that we've done that have produced ionic compounds, always be careful of writing the formula on the right side because you want to check the charges. So strontium is +2 and chloride's -1. So that means I need 2 chlorides for every 1 strontium. And so this reaction is not going to be balanced. One trick to help you with balancing it is that the H and the OH and the water all need to be equal to each other because one H and one OH make one water. So because you have to have 2 OHs here from the formula, I'm going to go ahead and make 2 H's and 2 waters because they all need to be equal to each other. So now I have 2 H's and 2 OHs, which makes 2 waters, and that would balance the reaction. Okay, that's the end of this packet here. I hope you found that helpful. Thank you.